Okay, good afternoon. It's time to start again with our fourth keynote speech, actually. Today I have the pleasure to introduce you Emtiyaz Khan. Did I say it right? That's very good. He's a team leader at the RIKEN Center for Advanced Intelligent Project in Tokyo. And he leads the Approximate Bayesian Inference Team. And today is going to talk about a very, very interesting topic. So let me thank him in advance. I will also thank him again afterwards. So Emti, the stage is yours.
Thank you. Is it on? Okay. All right. So yeah, thanks a lot for inviting me, giving me this opportunity to be able to talk to the people that I most care about. So let me say, I've been thinking about this problem for forever since I started my career. And so I'm going to talk about how to build machines that adapt quickly. And by the end of this talk, you will not be able to build the machine, by the way. So please don't over-expect. But hopefully I'll give you some ways to think about it. Start thinking about in the right way. So give you some fundamental principle on how to approach building some machines in the future. I think we are very far from it right now. So it's too much to expect that we'll suddenly have these things. But I will talk about principles on how to go about building such machines and what are the right problems to work on. So slides for the talk are available at my webpage. And let me just start by talking about the big picture problem, right? So continual lifelong learning. And the goal is to design machines that can keep learning for a long enough time by observing, interacting, adapting, and exploring the environment. And we see this kind of learning every day. We do it ourselves, right? Like humans are extremely amazing. And if you've seen my talks before, you've seen this video. So this is my daughter. This was like filmed like 10 years ago. The term continual learning didn't exist at that time, but I was already showing this in my class at the time, like how amazing it is that humans can learn on every day-to-day basis, on hourly basis, by randomly exploring the environment when we don't know what the environment is. It's very limited. It's a very small room that we sit in. It's not at all an IID data sample from all internet, right? But we are able to do something with it. This is remarkable. It's incredible, right? So this is after 6 months of that. This is 1 year old. Actually, she's here in Pisa right now, and she's still not good at ukulele. So there goes the hope for AGI. So she's learned something. She has figured something out what she likes about the world, and she's done this by interacting, adapting to the world. And she doesn't stop there. Every day there's a new thing that's going on, right? In their world, of course, right? So this was after 2 months of that, and then gone to a bigger instrument. So this is from ukulele to guitar, and she cannot hold it because she's small, but she has adjusted herself, used her previous knowledge, right? She's not like, she doesn't need retraining, thank God, from scratch, like every 3 months. That'll be very costly for me, right? So we have some mechanisms built in society for us to be able to live like this, learn like this eventually, right? To be able to absorb information over a long period of time and continue to do that. This is incredible. So when people say, oh, well, we got a big GPT model and it's conscious and all, and it's going to kill us someday, I say, come on, like, are we there yet? Not at all close. I mean, I don't even understand what's from internet these machines are learning. If you change a little bit, small things in the system, it can completely fail. So this is not a machine learning system, but it's kind of supposed to make you think about how brittle, how unreliable, how untrustworthy these systems are. If you want to fix something, like we are classifying some race of people as gorillas and we want to fix this, we don't know how to do it, We still don't know how to do it. So when people say this problem has been solved, this is not an important problem, it kind of pisses me off. in a way, right? Like, come on, like we don't know what the system knows, what it doesn't know, how to add knowledge, how to improve it over time. If something is broken, how to fix it, we don't know it. So for me personally, continual lifelong learning is the, one way to go towards sustainable systems that don't like give power to only a handful of people who can train these systems, who can have resources and can throw $1 billion every few months to build a new version because they are at war with some other company, right? We don't want this. We want reliable system that works well. We want systems that we know how they work. If something is broken inside, we can go in and we can fix them. And we can kind of guess how much, damage it will cost, how much, what kind of things will come out of after fixing. Will it work? We have to retrain from scratch and all those things. So I think continual lifelong learning is an important problem. So we're here for a reason, and let's continue on this. Let's not get distracted by it. Now, today, what I want to talk about is how to, stop worrying whether, I'm doing the right thing by doing continual learning, but start thinking from first principle about this problem. So let's try to think about some fundamental principles that will always come back. We will always fail, no matter what continual learning problem we are solving. Maybe it's a deep network, maybe it's a linear regression, but some things don't change. So let's start to think about those questions. And that will then help us to connect, combine, and improve some methods. And that's the hope. Okay. So I'm not going to show you some big numbers. I'll show you one such plot, but it's more about, the talk is more about thinking about the problem in a fundamental way and trying to establish important questions that we should be working on. So I'll start with a very big picture overview that I think is a general umbrella under which all these problems fall. It's distributed information over time and space. So whenever we are faced with this kind of problem where information is not sitting at one server, not one big data set, one big world that we can always go and sample anything from it, whenever the information is distributed, it requires dealing with interference. I think I use the word interference. I think Siddharth asked me to do it because I think it speaks to you, right? So we want to understand how past and future interfere with each other. And I will start with Bayesian thinking, but I will give a very precise notion of it as gradient mismatch because, maybe gradient makes more sense to this community. So I decided to do that. Then I'll talk about in the continual learning setting how to reconstruct this gradient mismatch. And we'll see that all sorts of methods can be seen as doing this reconstruction. Okay. Then I will go into how can we build machines that do quick adaptation. From here, we'll see that it's about where the mismatch is. It will turn out to be the mismatch actually being caused in only a few examples. And it depends on the future. We don't know it yet. But we can make certain bets and we can think about some kind of representation of the past. I use the word memorable past or memory to say that, and we'll try to think about that a little bit. And in the end, we'll see that if the difficulty of this quick adaptation, it will boil down to how many points have mismatches. If there are too many points that have mismatches, it's a hard problem. If there are a few points that have mismatches, it's a simpler problem. And this gives us a way to then approach the problem divided into smaller parts so that things are changing in a nice fashion. Okay, so that's the kind of overview of the talk. There's some of the papers that I will cover are here. But I will also show, one ImageNet result, which just to keep people happy. If you think that this doesn't really work at large scale and like, oh, you're talking about philosophy and stuff. Well, we're doing real work and sometimes it works to some extent. So I'll show a result on ImageNet where by combining EWC, functional regularization and replay, we can get quite good result with just a little bit of memory, like just 7.5% of the data have to be stored. The poster is actually after this talk, so it's very well located in time. Okay. Okay, so I've used some time and so okay. So let me start with the big picture, the view of these problems. I actually think that a general way to think about these problems is to think about distributed information processing. And the information is distributed over time, sometimes over space. So like continual learning, the data is sequentially coming in and you are updating your model, right, slowly over time. So this is not a graphical model. It's just showing how the information flows and you're updating. So this one contains both the data D1 and D2. So I call it theta 1 plus 2. Then we go to add third data to it, D1 plus 2 plus 3. This is like continual learning or sequential learning. This looks like that. But there's also information that could be separated in space. So you can have two local clients with two data sets, and each client kind of processes the information locally, gets some parameters, and then sends it to a central server, which combines this, and then they iterate. And eventually the hope is that somehow this model would be the one that's trained on both the data set, right? So the key idea in thinking about these problems where the information is distributed over time and space is that we must be able to distinguish what is new and what is old, okay? So if you learn from D1 and then you go to D2, you need to think about, is D2 very similar to D1? What is new in D2? And how can I take that new information and add it to my system to get theta 1 plus 2? Okay, this is actually very simple intuition. And there is a very nice way to think about it in a very principled way. So the intuition goes like this. If D1 and D2, they're very different from each other, then if you combine both the data sets and learn jointly from it, so theta 1 plus 2, that should also be very different from individually learning on it, right? So if you just use the data D1, that should give you very different result than theta 1 plus 2. Somehow this change is big. You have actually heard of this principle. It's not presented in this way, but it's kind of one of the fundamental ways of Bayesian thinking. And I have put two papers here, but the idea goes back to Gibbs, with Gibbs distribution and all that. Basically, you're defining new information by measuring the gain or change in the posterior distribution. Okay, so something like doing a KL divergence. You say, I have a posterior on data 1, and then I add data 2 to it. So I get a posterior on both the data sets. And this gain, this change, if it's large, then the information is new. And if the change is small, then the information is not new. Okay, so classical algorithms like Kalman filter and hidden Markov model, they actually are using this principle to do an updating. But I know people don't like Bayes, and maybe in this crowd, there are very few Bayesians that I see. So what I want to say to you that you don't have to think like a Bayesian. Maybe it's always there, but you can just think about the log space of this KL divergence. So you can think about differences between these parameters. So if you go from theta 1 to theta 1 plus 2, you add the data D2. If the change is big between the parameters, that means that it's very new information. Or you may think about the prediction of these models, and you can see maybe the second model predicts very differently from the first model, right? And so this is kind of how we think about it. We think about change and gain in the information to define what is new and what is old. So I'll try to present a very simpler way to quantify this change in terms of gradient mismatch. So basically say that this difference is, in some cases, is exactly equal to gradient mismatch of some kind. But remember that there is an underlying Bayesian principle. The work that we actually do in our group is basically trying to build posterior approximation so that you can go from here to there, and you can kind of connect back always to the Bayesian principles. Okay, so I will not use the word Bayes maybe that much from now onwards, so don't worry. Okay, so we'll just work with this thing. And let me just take the first example of model merging, because, well, we're in a continual learning conference, but talking about model merging, because I think this is a simpler setup. It's kind of makes thinking about these problems a little bit easier. We'll try to connect inaccuracy of model merging to gradient mismatch. And there you can see how this all works. It's in this paper recently published. Work was done by Nico Daheim, who is a PhD student at TU Darmstadt, and Thomas Mollenhoff, who's a research scientist with us, and also other senior folks whose photos I didn't put here. Okay, so let's start by, let me define what this problem is. Okay, so what people do in model merging, this is really, really popular in this LLM era, that you have a large LLM or a pre-trained model, and you'll start from there, and you will fine tune on a data set D1 to get theta 1, and you'll fine tune on another data set to get theta 2, okay? So you can think of it like it's a English language model that's been learned, and then you fine tune on Spanish and you fine tune on French, but actually you want it to translate both. So eventually you want to merge these two fine-tuned models to get somehow closer to the model that's trained on both languages, right? But training on all things is very expensive. So they just do this fine-tuning and try to add it. So information flows in this way. You can think of it as like one-shot federated learning. There's no going back after merging. You just take theta 1 and theta 2 and try to merge them such that you're close to theta 1 plus 2. Okay. Feel free to raise your hand and ask questions, by the way. It's not clear. It's going to get very mathematical very soon. Okay, so what they actually do, their simplest strategy is to use just simple weighted average. And this sounds really insane when you think about it, right? Because it's a really large model, billion parameters, and you just add the parameters. And then they say, oh, wow, it works. Large, deep networks are crazy. They're amazing. They're linear somehow. It's great. Yeah. So when I heard this, I was like, oh, this is a perfect place to apply what we already know about gradient mismatch. And so this paper was born out of 10-minute discussion that we had last year in Japan. It's quite nice. So I basically said, oh, well, the quality should depend on how far these things are, right? If we think theta 1 plus 2 jointly trained model, if it's not that far from theta 1 and theta 2, then perhaps you can just combine them. So if this quantity is small, then your model merging should work well. If this quantity is large, then this model merging should be difficult. So we should be able to see this in practice. And then we'll think about causes of this mismatch and try to improve it. So that was the plan that we set out to do. For simplicity in the talk, I will just assume alpha 1 and alpha 2 to be 1. But you can do this for any alpha, okay? So just see the paper for that. It's this paper at ICLR 2024. Okay, so next is the slide. That's the heaviest slide. And I tell you, if you make it through this slide, you know this talk, huh? So just stay with me for next 2-3 minutes and we'll get through this, okay? So I will do a very simplification here. And if you think that this is very restrictive, fine, but this is not, there's a more general principle, something to do with Bayes and all that. So I don't want to present that right now because the paper is not out yet. So let me do this modification. I put an L2 regularizer, okay, in this. So this L1 is on data D1, right? Depends on the data, but I add a regularizer here because it makes the math simple and it's easy to appreciate for you. So please bear with that, but it's not necessary, okay? So it's not a limitation. It just makes things not much nicer, okay? So we're gonna train our models, fine tune our models. Well, I'm not gonna look into fine tuning right now. I removed LLM from it. In the paper, you can see the general setup, but just think of like one problem trained on data D1. There's no LLM right now. And let's think about this. So when you try to solve this problem, let's say you train and you reach the minimum of the problem, then you're at a stationary point, right? So I've just taken the derivative of this and derivative of this. So I get this stationarity condition, basically gradient plus the parameter that comes from this L2 regularizer. And I could just rewrite it in a slightly different way. Okay. So basically, I've just moved it to the other side, right? The gradient. So I'm basically saying parameters are gradients. So just remember that. Okay, the parameters are gradients evaluated at that parameter itself. So This is kind of a representative theorem. So if you know SVM and stuff like that from old times, it's kind of an instance of it, but written in a very simple way where, I've assumed that loss is differentiable and all this. So the duality will come at some point, very briefly mentioned. But think of parameters as gradient. Okay, so once you know this, then you know that difference between parameters would be difference in the gradient, right? And that's how gradient mismatch comes in. So let's keep doing this thing. So for theta2, let's assume the same thing, right? And we can then again look at the optimality condition and write parameters are gradients. Now it's at data 2, right? So this is D1, this is D2. Okay, these are two different gradients on two different loss functions, right? But when I do joint training, I want to train with both loss functions together. I still have the regularizer, right? So I could apply the same thing here. Here, the parameter, the joint parameter, composed of two gradients, one on D1, another one on D2. Are we cool with this? Any questions? You're fine, right? Oh, there's a question. Sorry, I'm not able to understand. Sorry. Oh, sorry.
So my question is that theta of 1 plus 2 is a multitask learning, or how do you train it in a joint way?
Multitask learning?
Yeah.
Like you have more losses, you mean? Like more?
So the theta 1 is one task, right? So for example, learning English, and theta 2 is learning Spanish.
Oh, yeah, I'm not doing that right now. So you're right. So I'm assuming that's the same architecture. It's like you have a big, large language model, and then you fine tune on it. So it's always the same architecture. So theta 1 and theta 2 are same model, and they're trained on like language, let's say. So
and how do you train the last one?
Oh, the last one is jointly. So think of this as like Spanish and French.
Together.
Yes. That makes sense?
Yeah.
So theta 1 plus 2 is able to speak both or translate both. And theta 1 is only Spanish and theta 2 is only French. Does that make sense?
Thank you.
Yes. Yes, I so very quickly mentioned that. So that's covered in the paper. But here, to make math simple, I removed it. The math still goes through, even if it is not. Think of like two linear models, then it'll still work, right? Two logistic regressions, you can still do it, right? So that case is covered in the paper. So have a look at that.
Hopefully a quick question. When you say the first line, when you say theta 1 plus 2 equals the argument, you don't say the loss of 1 plus 2. You say the loss of 1 plus the loss of 2, right? And if that depends on the structure of the loss. So are you assuming something about the loss?
Yeah, we're assuming usual ERM style thing, like sum over data points in D1, sum over data points D2. So that's why they summed up, but you're perfectly correct on that, what you're saying. Yes.
We have another question, perhaps another one.
Okay, I haven't lost everybody. That's great.
Thanks. I have a question about the evaluation. So in previous slides, I saw that it's the difference between theta 1 plus 2 and theta 1 plus theta 2. Would it be more reasonable to evaluate this by the output of the model?
Yeah.
So it should be the function parameterized by
it's coming.
Plus 2.
It's coming. Yeah, you could do it. But actually, they're two sides of the same coin.
Yeah, because parameters. So how do you say that? A function being similar or pretty close to each other doesn't mean the parameter themselves are close to each other.
Yes, you're right. It's coming. Okay, almost another one. Quick question, almost not like hard questions.
Might be hard. I'm sure it all works in a proper Bayesian way, but your model and your gradients are parameterization dependent. So under reparameterization, you'll get an equation that isn't theta 1 equals minus gradient.
It won't work, yeah.
So you're kind of hoodwinking us a little bit with this slide, but I'm sure it works really.
Yeah, it doesn't work actually. Yeah. I mean, why model merging is working is because things are close by. That's what I'm trying to show, right? There's no magic. Yeah. So we are actually really analyzing a very simple problem that where we can tell how far things are, and they're kind of close. Things don't change much. Okay, so then things work out. So, but we start to think about this, you know, and we don't like overclaim and say everything is possible. That's what my hope is. I would never give this kind of talk at NeurIPS or anywhere else, right? This is the place that chose very deliberately, go so slow and not present everything. So I'll hurry up soon. And okay, so we've gone through this. I guess we have achieved something. So what I've just done is I've written those three equations now all together. Okay, so you could see, right? Like, so there's two separately trained model and then one is jointly trained model. And I have 4 gradient terms here. And now I just want to write the difference that I want to see. So like the jointly trained model minus the sum of these. So I have set the alpha to 1 just for simplicity, but just do this, right? And if you do this, then you see, right? So there are 4 terms in the right-hand side. So you get 4 terms, and I have rearranged them. Okay, and I've rearranged them, and I basically, the first term I've said is the gradient mismatch on the data 1. Okay, because it's L1, L1. Okay, and essentially now what we are faced with is that future, the new model, theta 1 plus 2, somehow its gradients, or predictions, if you want to say, have changed from the old model theta 1. So this is only on the data 1. So for data 1, we only have to care about theta 1 because theta 1 is trained on data 1. But the same thing happens on the second gradient mismatch term. Here is the gradient mismatch on data 2. Like theta 1 plus 2, somehow its gradients are also changed from the old model theta 2. Okay, so we are facing 2 gradient mismatches here. So the future somehow affects the past. There's 2 models, theta 1 and theta 2. And the future is theta 1 plus 2. It's different. It somehow departs from both of those things. So somehow if the gradients change a lot, then this difference should be big. Okay? So the question about whether we should use parameters or function values, it's all in there. You'll see the function values when we start to dig into what gradients are. But gradients are actually made up of function values, and you'll see the predictions come in there. But this is exact, right? This was really beautiful when I wrote it down. I was very happy because it's kind of, it's exact. You know, I've made very little assumptions, and I can start from this, and I can add this pre-trained model. I don't have time to talk about the multimodal thing, but we could talk offline about it. But you could do all sorts of things and permutation and all those things. But you see that this is very simple calculation where you can write the change in the parameter space in terms of the gradient mismatch. And this is what I was trying to show. Let's now gain further insight by looking into a very simple problem. It's this logistic regression, okay? And what I'm showing you here, there's 2 classes of data 1. And there's I've learned a model, theta 1. So I'm not showing theta 2 for simplicity. I'm only going to show mismatch on D1. And what will happen as I add D2 to D1, as D2 departs from D1, we'll see that the classifier will move a lot. Okay. So that's what's being shown. So D2 is this light color thing here, right? And as it moves away from D1, the classifier moves a lot. This black line is theta 1 plus 2. And you could see that gradient mismatch is actually not big in the beginning because there's a lot of room and no gradients on the data points have changed. But as the line moves away, it starts to interfere with the past predictions, with the past gradients here and here. And only then the gradient mismatch starts to become bigger, right? So the problem would be easy as long as the gradients on the data examples are not changing. And the problem becomes harder as there's a huge change. But the change actually is localized somehow. It depends on the future, and it's localized at some kind of boundary. Okay, so there's still hope if we were to reduce the mismatch. Okay, so we'll now just, from now onwards, we'll just work with this one equation. Okay, so what we'll do, we'll take this equation, And we'll focus on minimizing the gradient mismatch, so reducing the gradient mismatch. And we'll see that all sorts of methods can actually be seen through this. Okay, very, very simple strategy we use, which you know, it's just Taylor's approximation. So we'll just write this guy, right, in terms of that guy. And this is the Hessian, second derivative. You know this. This is Taylor's approximation. Okay. So I rearrange it. I get that, right? I get that approximation. And then rearrange for this guy, similarly, you get another one, right? And if you will manipulate this, and you can trust me on this, you will get this merging strategy. Here now you're not just doing theta 1 plus theta 2, but you're weighing by Hessian or Fisher if you wanted to. I mean, it should remind you of something that you already know in continual learning, right? Which some folks have actually written papers on. We call it EWC, right? So, but you know, they're rediscovering these things in that different world, where they don't call it EWC, they call it merging models with Fisher weighted averaging. Okay, but it's actually just doing Taylor's approximation, and it's same mechanism. It's minimizing gradient mismatch by doing this thing. So I will show this on continual learning, and EWC will pop out by the same mechanism. It will not be surprised, but it was kind of funny for me to see this in a different world. All right, there's a question there. Could you give it to Donna?
Yeah, this is really cool to see, actually. Makes me understand some things that I don't think I understood before.
Yes,
so
sorry.
thank you for that. I want to question whether minimizing mismatch is always necessary. So if you think about, you know, maybe that theta 1 was learned based on a whack load of data, and so therefore it's a very good parametrization, and therefore we don't want to perturb it, right? We want to retain it. Then yes, reducing the mismatch is good. But if theta 1 is something, and then the second data actually brings some insight, right? Then maybe doing this is not so good. Is that?
Yeah, it should be like that. So I mean, if you're setting up your problem right, then the second term should be bigger than the first term. That's how it should be right now. Okay. So yeah, this is a principle. Again, I said, like, you won't know how to just suddenly download the code and run this, but this gives you a way to think about the problem, that you should look into this alternate view. When you change your parameters, something happens on the data, and that's the dual view, where it helps you to understand what the model is actually doing in the data, how it's changed, and what parts needs to be fixed. That's kind of a very simple thing. So, okay, so we have in the paper, actually, we showed lots of existing merging approaches can be all kind of written in this way. Okay, so if you read the paper, you'll see that. One cool thing that we had was this very nice experimental validation to show that if you reduce gradient mismatch, it also reduces test error. So, you know, when I talked about this, I never mentioned anything about test. I never mentioned anything about out of distribution, in distribution. No assumptions, right? Just an L2 regularizer added. And with that, I have deduced that gradient mismatch should somehow reduce the difference between the parameter. But actually, if in reality, when you do the experiment and you do brute force retraining, so like you have, so in this case, this is on Roberta, you have 5 fine-tuning tasks, and then you basically you retrain by putting all of them together, and that actually reduces the error. But you can also kind of see that the gradient mismatch is also reduced. Okay, so gradient mismatch actually correlates with the test performance, and kind of the theory, it validates the theory in this way. If you go in the paper, you'll see more experiments like this. Okay, so I have used about 36 minutes now, and now I'm getting to continual learning. So I have to really, really speed this up now. So next part, I will go very quickly. This was actually done with Siddharth. So originally, we came up with this this idea of gradient matching and reconstruction in 2021, but nobody knows about it and nobody cites it. So great. But this work was very important, and Siddharth is now looking for a faculty position, and he's very good. So you should hire him. Okay, so So, okay, so I'm going to talk about this, but it's kind of almost goes in the same way. Okay, so you do the same thing, right? You write down the problem on individual loss, and then you write the problem on both the losses. Okay, so there's no theta 2 in this case in continual learning. You learn something on D1, get theta 1. Then you learn on something on D1 and D2, you get theta 1 plus 2. So you do the same thing, you subtract, right? It's quite straightforward, and you get that, right? And here you can do the same thing. You say, oh, well, it's gradient mismatch on data 1. Okay, and again, the somehow addition of this data 2 is interfering with the past. Okay, and it's through this gradients that needs to be adjusted now. So so the new loss is doing this, and now we have gradient mismatch of the past data. Okay, so well, what should we do? Well, we kind of suggested this strategy that let's now try to find a regularizer such that its gradient somehow matches this term. This is somehow the discrepancy between, okay, so what I've done actually, sorry, maybe I skipped this, but what I've done is I've taken all of these guys to the other side and made this equal to 0. Okay, so just moved all of those guys here, and I've just rewritten it as a stationary point of a new problem. And I'm saying that let's try to find a divergence that will minimize the distance between the parameters, but also the distance between the gradients. So you see, this is not just parameter space, but it's also the function space in some way. And you'll see soon function space coming in, but they both are important. It's not just one thing, okay? And don't let people fool you the other way. If they say that one thing is better, sorry, if you're working on that, no offense to you, but I'm happy to talk about that. But that's one thing, big thing that I want to push for is to not to let the community go in the direction that I don't think is the right way to go. Okay, so we said that let's write the problem in this way. So it's right. So I have written this part is just L2, and then this part somehow we'll find some kind of divergence that will whose gradient will match at the stationary point to be this. And what we argued in the paper, it's a very kind of compact paper with lots of things in it, and that's why I think it doesn't get cited that much. But we showed that all sorts of these methods, they can be basically seen as different divergence functions. Okay, and these methods are like, you know, the classical ones, the EWC paper, but also papers that people use in functional regularization and then knowledge distillation and doing dark experience replay that everybody's showing on their slides. But also classical stuff from 2001 on SVMs and how to do knowledge transfer. And this was done in dual space. So it's very weird to find that here in the primal space, right? Work by Wapnick, which you should read if you haven't read, Similarity Control. This is beautiful work, okay? And gradient episodic memory that actually is connected to this, but also work in Bayesian setting. This is work on Gaussian process, very, very popular work. All of this falls within this framework, okay? And I don't have time to show all the math to you, so I'm going to skip all this, but I'll show you a favorite one, the simplest one that you know, right? So we'll do the same trick. We'll just do the Taylor approximation that we did before. And if you did that, right? If you did that and you rearrange this term, we'll basically put these things together, you get this, right? And you try to find a regularizer whose gradient is this. And you know what it is, right? It's just L2 regularizer that we use in EWC. Okay, so you don't see EWC as doing some kind of gradient replay, but it is actually trying to reconstruct some kind of gradient mismatch. It's trying to adjust those mismatches by using a very static, you know, Hessian approximation that you cannot change. Okay, it's different from experience replay, but like but it's not really. Okay, so in the paper, we go into a lot of details. So I have about 20 minutes left, right? Yeah. Yes, good. So, yeah, okay. So if somebody asked about functional regularizer, you can go in the paper and you can check out what actually happens is that if you assume certain kind of loss functions, like let's say least squares, like squared loss, or any generalized linear model, then you start to see this function output come in here. And if you write down the gradient of this, you start to see function predictions, right? Prediction error come in. And so if you plug in this gradient mismatch, this guy, essentially the difference in the gradient is the difference in the function outputs. Okay, so the gradient mismatch is actually related to functional regularization if you assume that somehow your model is linear. And that's where the problem is. Huh? People don't realize this. NTK is great, but it's linear. Okay, so you may say that it's not, but no, it doesn't really work. So actually, you can write it like this. You could say functional regularization, fine, but assume that it's somehow it has assumed linearity inside. If you want to fix this, okay, before fixing, let me also say that this kind of work was done in SVM with dual problems, where people were simply writing this functional regularization. So phi is the feature vector. And basically what I've done is do this with one hand. I've just written this guy because it's linear. So just written phi theta. And you can actually invert it. You can write it directly in function space by using duality theorem. Okay, so that's how we connect these gradient mismatch things to the work that was done in kernel methods in SVM and lots of opnics work. It connects directly through duality. Okay, so you can write the problem completely in function space, but beware that this assumes linearity. Okay, so the poster that we have here is really trying to show that there is another part that's being ignored. Like, for example, if your data has label noise, and if you made some mistakes in the past, this functional regularization is going to really hurt you in the future because it's only looking at the prediction, but it's not looking at how wrong this prediction was. Maybe the data was wrong. Okay, so if you actually do the math, I'm sorry, this is impossible. I think even people who wrote the paper cannot follow if I show this, but it's like this, you know. So, okay, sorry. So the difference is that the feature is not fixed. Okay, if the feature is phi I, it doesn't depend on theta, then you're fine. But in neural network, it does. So the Jacobian, they change over time. NTK is not working there because it's assuming somehow the feature to be constant. So if you do the math, you have to somehow get around this being different, and you do all this, you do all of this. And then you can write the functional regularizer, but you can show that the label noise will hit you here. Okay? So there is a term that's missing in the function space thing. So function space variational inference or function space regularization, all of this stuff, I think a little bit be aware of these things, that they're a little bit incomplete, right? So we need to play with this. Okay, to summarize this slide, I showed you weight regularizer, right? Reducing the gradient mismatch, functional regularizer, and their dual version, assuming some kind of linearity in the feature. The feature is somehow constant. But if you want to deal with features that are changing, you need to do some kind of replay. Okay, so these three things are complementary, and they do different things. And actually, if you're a Bayesian, then you love this because you realize, oh, wow, it's actually uncertainty in the weights is the weight regularization, uncertainty in the prediction is the functional regularization, and uncertainty, aleatoric uncertainty, label noise, is the last thing. So it really it all makes sense, you know? Sorry, okay, maybe there's a very hard questions coming here.
You know, replay isn't the ultimate gold standard. Can you explain that to me?
Oh, yeah. So sorry, I had this in the slide, but I went very quickly over this. Very, very good question, actually. So replay is the ultimate thing. Replay is not reusing the old solution, right? Yes. So what we would like that if we have trained on something, we have learned theta 1, we shouldn't throw it out. We should reuse it. So what would be great is to do replay on the parts that need adjustment, but also reuse theta 1. We're getting there. That's the key to combine it. So there are many ideas. We did one thing, but we shouldn't throw out things that we have done in the past. We should reuse them, is what I'm trying to say. Does that make sense? Right? Yeah. let's talk offline about things you disagree. So yeah, I know many things I'm saying. This is may make sense from my side of the world, but I want to hear your side maybe after I finish doing this thing. Okay. All right. So what I'm saying is that the optimal combination of these three things, it depends on the task and what are the general principle and how to combine this. We should look deeper to the source of mismatch is what I actually found. And I think the difficulty of adaptation, and this is the last part, and this is very light. So just sit back for next 10, 15 minutes, and I'll try to go very quickly about it because this is mostly intuition. But this is a very hard problem. So as you see that we need to somehow minimize the mismatch, we need to think about choosing the examples to regularize now in the past. But we don't know which example to regularize because we don't know the future, right? In the future, something's going to change, but we don't know it. So we have to now make certain bets. We have to think about presenting our current knowledge somehow so that we can protect our knowledge from interference from the future. Okay, so this work was done on memory, was done by these 4 people from our group. But actually the original idea was by many people, including Siddharth was a co-author on this when we first discovered this in 2020. So actually this was an early idea in 2019. And at the time, we didn't really know about gradient mismatch. So I was actually very impressed how right we were from the very beginning to think about the difficulty of the problem. And at that time, we thought, oh, we want to protect some knowledge in the model. So why don't we just like try to, store certain data examples, perhaps at the boundary. And at that time, we didn't know what boundary meant, right? And then try to force it to be, the predictions to be the same. Let's not change the prediction of those points, but retrain on the task 2. Okay? Then store some more boundary points and then retrain again. Okay, so that was the idea that we had at the time. We didn't know how to define the boundary, like what shouldn't change in the past. That was not clear. But through some simple math at the time, we started to come up with the criteria, and it's actually quite nice looking back 5 years later that it actually was the right thing to do. So we were actually looking at this kind of mismatches, and we were doing a Gauss-Newton approximation. So this is similar to the functional regularization. And that's why this paper title has functional regularization in it. But essentially, we used very simple criteria to say that some points are at the boundary and other points are not. And this is basically like you do forward path through your network and just look at the prediction and just sort example with that. This was very, very cheap. But already we start to see this kind of pattern. Points that are very regular, they're kind of far from the boundary. Points that look kind of crazy, right? Maybe for some reasons, like 4, that's kind of 7 maybe, or these are all crazy things. And it seems like that, oh, they are close to the boundary and they would most likely get hurt by the change in the future, right? And we kind of figured that this is somehow related to leverage score and influence function, and we actually wrote about it in our paper in 2020. It was quite nice because that turned out to be, one of the right way to think about it. So what essentially happens actually is that it's like what people did in support vectors. So, it all makes sense. It's not very different. There are 3 kinds of support vectors, right? One that are easy. So like if you're correctly classified, right, you're in this side, then you probably don't need to represent it very well. I'm kind of doing average thing with Hessian. That's fixed, static, doesn't change with time. That's fine. Let's do something like EWC for those. But examples that are really at the boundary. So this is correctly classified, but if you change the boundary a little bit, it will be incorrectly classified. So somehow uncertainty is high about these points. And these points actually go well with functional regularization. And then you think about the points that are weird points that are on the wrong side of the border. Okay, and these points are maybe misclassified, and they're atypical and they're outlier. We don't know why they're misclassified. Maybe they're outlier. We don't know. But the model thinks that this is on the wrong side. It's fine. I can deal with it. And these kind of points can actually really come and hurt you in the future. So you have to deal with them by using replays. That's how it comes out to be. And just to show you in the end, right? Like you can again rethink through this very toy example, how those things will impact, right? We are really thinking about what is the boundary. And the boundary kind of depends on what's going to happen in the future. So if your line is changed that way, it's going to start touching things here. So those are the points we need to protect if the future was this, but we don't know the future, right? So this is what we actually, so the paper that you will see today in the poster, we start to think about this and we say where the gradient mismatch is low, let's try to split those points and just do a EWC style approximation. Where the mismatch is high, let's do functional regularization if there's no label noise, so there's no label here. But then let's try to put, this is not experience replay, but this is slightly different kind of replay. So because it's reusing the old data, let's use a separate memory of those points where we suspect some kind of noise to happen. Okay, but still the problem is not solved, and this is why we don't know how to design machines that can adapt quickly, is that we don't know the future. So we can't choose these points beforehand. And so the problem reduces to figuring out the memory and this kind of split. Okay, but still, maybe you could just randomly choose these points and see what happens. Okay, so that's this paper. There's a poster, it's J6 today. Come and talk to me and Siddharth for that poster. But there we just use random memory and try to combine like EWC, functional regularization, and replay. And what basically happens is that if the memory is very small, then you go back to doing something like EWC. But as the memory is increased, you start to improve over it. Okay, so you start to do these tweaks at some points. Again, this is random memory, but still it actually pays off. And 7.5% is very, very little, by the way. I mean, ImageNet is million example. You can do the calculation from there, but it's not that big a memory. So I think that this style of thinking, by choosing this memory more carefully, we should be able to push the x-axis this way, right? And hopefully push the y-axis a bit more up. So the hope for us is to get some performance like 1% data, get performance very close to batch, and that would be satisfactory. We're not there yet, but I think we are making progress on this. So we've been working on memory, and I'm gonna maybe just very quickly say, I'm gonna skip the math. You can read the paper about it. But for me, I think representation, memory comes out to thinking about sensitivity. Okay, and this is a very deep connection with Bayesian methods, which is very comforting also. So we are basically trying to say, let's protect the model. We don't know what's going to happen in the future. So let's just think about what could happen in the data that we have right now. If we only have D1, let's try to find places where we can delete some data and try to, maybe if the model changes a lot at those places, then try to store those places. Okay, and that's how we define the memory. Math is actually, again, comes from this, by the way. So you just start with the same equation, you apply to your own like data right now, that's your future, and you do, and you get influence function. It's not, nothing is magical. It's just all very, very, very cute and very printable. Like it's all one equation that says everything and all makes sense. So we do a lot of work on this and trying to figure out what past has most influence on the present. And you can do this in like, you don't have to think about like stationary point. You can do this on algorithms. You can do this on trajectories. And there is a very nice paper, this one that we did, and you can actually compute some of these quantities very cheaply, like just compute prediction error multiplied with prediction variance. These are the two causes, like 3 points I showed you, the points that are close to the boundary and there are the points that are outliers. They're covered by this. So this kind of helps you to do this thing. Okay. So I have like 6 minutes or 4 minutes. 6 minutes maybe, yeah, because we started a little bit late. So, okay, so that was the talk. Okay, so we're done. So what I showed you, okay, so distributed information over time and space. You have to think about interference, right? And I hope the talk has given you a little bit more precise notion of what interference is. it can be thought of as gradient mismatch or some kind of reconstruction of it to deal with this mismatch. And if the mismatch is only at a few points, right? If the sensitivity, if your model is very robust, right? Then it's somehow we know it's easy to adapt to the future because we have enough representation of the past so that we can tune the prediction of the model or the gradients of the model at a handful of examples. And maybe that's how kids learn. They are only doing small updates in their brain when they see a new object with different color, a new toy, a new image, a new thing, right? So the hope is that quick adaptation is possible when you're able to keep these mismatches to a very few examples. And difficulty really lies in trying to be able to find these points, okay? Just 1 minute in the end, I want to say, lifelong learning is possible only when each subtask allows quick adaptation. So the way that we do continual learning right now, I think it's not correct, because I think a big thing is order matters. You may, so like I've given you a way to think about this, like you can, if you go from task 1 to task 2 and the gradient mismatch is really huge, it'll take really long time for you to recover, and you may make a lot of mistakes. And those mistakes you'll carry throughout your life, and it'll make future learning harder. So if you want to create a benchmark, you could go there, you do these training from scratch, these subtasks, and you can choose, you can order them in such a way that easy tasks come first. Okay, so it makes the order should be chosen properly in our benchmarks. And we can do it by looking into gradient mismatch. Somebody should do this, create a better benchmark. So we should also allow revisiting and fixing mistakes, because some mistakes that have been made, right? We don't know in the past, and it just makes sense to do that. And I think we should be thinking about good methods and bad methods in terms of revisiting frequency. Like we should maybe somehow allow like linear to log linear revisiting frequency. In the worst case, it should be same as batch. And that's how we should measure performance. And I'm happy to talk about this more with you. But what I have learned is that memorable past really matters. I think that's where difficulty is. And that's why I give up on solving continual learning next year. And you should too. Let's not solve it, right? Let's make meaningful progress. Let's figure out what is easy, what is difficult, what kind of benchmarks will drive the next set of goals that we want to do, right? But I really believe that harder problems require larger memory, right? But I also think that larger memory makes the problem easier. Okay, so you can store a lot of things and maybe still not like just do experience replay, but try to reuse old solution and try to revisit, reduce the frequency of revisiting, and maybe there's a better way to do these things. So okay, so we've been just thinking about this thing with the base duality projects. Just wanted to show you lots of funding, thanks to the government for all of this. That helps us to continue on this. We do a workshop on lifelong learning. The name is base duality, but it's actually focused on lifelong learning. Lots of folks who are here now, they were actually visiting just in June. So we do this every year. You're welcome to come and join. So please let me know if you would like to visit. We have some funding to invite some folks. And thanks to the group that has been doing all this work. So thank you for listening.
Thank you very much for this very interesting talk. I think we have time for one question or.
Okay. Oh, okay. I'll go ahead. So I have a question about the. Thanks a lot for the talk, and I like this stuff quite a bit. But for the gradient mismatch, and I think it comes back to your question about building the curriculum with the ordering, and I think that's why it doesn't work. So are you worried that you're just, if I understand correctly, you're looking at the magnitude of the difference between gradients? Shouldn't the angle matter? I feel like those provide you different information, and I feel like somehow the formula, the way it is, it makes a mistake because it just looks at the magnitude, which some sense correlates with the error. So you could in principle just look at the difference and look at the difference between the losses, and that doesn't work.
No. That's not the case. So yeah, I mean, I'm just looking at the difference in the parameters, but you can also measure this in the loss space, and then it'll go through a Taylor series where there will be inner products between the gradients. So it shows up. Maybe I could tell you later. Yeah. So it's not.
So the angle is accounted for
It's
somehow.
there. It's there.
Separately.
Yes.
Okay.
It's there.
It was short, so we can take another one.
I'll do a very short answer.
Very short, very interesting actually. What you wrote, order matters. I do subscribe, what you say. But I frankly miss what could be, your proposal for such an important issue.
Sorry, what is
the basic idea for capturing the importance of order in task?
Yeah, I was basically saying that, yeah, like, it's like, I mean, for me, some things, okay, so there's a bigger Bayesian way to think about these things, and it actually connects with what I was talking about in the morning today. But, somehow the problems that are easy, in those problems, the order doesn't matter that much. And the problems that are hard, in that order matters a lot. So like if you're in a maze and there's only one way to solve the problem, and it's very long, so it'll take you a very long time to find that. But if it's a simpler problem, there are many ways to go there. And this kind of comes down to, in a Bayesian way, it comes down to the volume of the posterior. And it also comes down to gradient mismatch. Okay, so these things are all connected. So that's how I think about it. And maybe we could talk later a little bit more in detail, and I can tell you more. Okay.
Okay, let's thank the speaker again. Now the poster session is starting. We have papers from the main track and the journal track right outside this room.